Hello everyone, so my name is Benjamin. I'm a PhD student of Gregory, and I also work with Satya in LPTMA. So today I'd like to talk to you about constraint stochastic processes, and more especially how to generate them. So first of all, let me say that this work was done in collaboration with Gregory, Satya, and Henri, who unfortunately could not be here. By the way, let me thank also the organizer for letting me talk here. It's a pleasure to be here. So I will talk about a series of papers here, recent work on generating those stochastic processes. But first of all, let me give you a bit of motivation. So free Brownian motion in one dimension is a stochastic process whose position x of t evolves according to this Hausberg d theta of t. And we give some initial position which we set to 0 for simplicity, is the diffusion coefficient, and theta is Gaussian white noise with 0 mean. So generating one-dimensional Brownian motion is easy to do on the computer. One discretizes the equation, and then one has that the position at time t plus delta t is time increment equals the previous position plus here Gaussian random variable with 0 mean and variance of delta t. So letting delta t go to 0, we converge to Brownian motion. Okay. Now, say that we are only interested in some trajectories of Brownian motion, called bridge trajectories. Bridge trajectories must satisfy the condition that the process at time tf, which is some fixed time horizon, comes back to the origin. So these trajectories, called Brownian bridges, are interesting because they have application, for instance, in behavioral ecology. Imagine here you have like 5 deers walking in the forest. If you look at their trajectories in the 2D plane, you see that they tend to come back home after the day, and therefore those trajectories are interesting to see. The main question from a simulation point of view is how to generate those Brownian bridges. Naive idea would simply to generate free trajectories and discard the ones that do not satisfy these bridge conditions. However, these trajectories are rare, and therefore they occur with low probability, and this would be a waste of computational resources. So the question is there an efficient way to generate those Brownian bridges? And this is a long-standing, this has been studied for a long time ago, and there is actually a mapping that can be done between a free Brownian path, x of t, with a bridge one, through this formula. Tf is fixed, and t is the time. Now you can check by letting t equal to 0 that you recover the initial position of the process, and when you set t equal to tf, the final time horizon, you get the bridge condition, capital X of t equal to 0. Next, you can convince yourself that this is effectively coming up with the right statistical weight, because it's a linear combination of a Gaussian process, so it remains a Gaussian process. And so you can compute a 2-point correlator and check that it corresponds to the bridge Brownian motion. Now, this construction is somehow fortuitous, and it happens only for bridge Brownian motion, and so we can ask a more general question: is there a more general method to generate such sort of constraint processes? And so this was a question that was asked by Dub, and he found, Dub was a mathematician and found the Dub formula. And more recently, this was highlighted more from a physics point of view by Satya and Henri, and found that a simple way to generate Brownian bridges is to write an effective Langevin equation. So this is the free Langevin equation with an additional term that is an effective potential induced by the constraint, and that simply looks like this. So this is a quadratic potential whose intensity grows as time gets closer to Tf. And so they've shown that this effective potential indeed covers Brownian bridges with the right statistical weight. And so this is quite a nice picture. They found also that it also works for other types of constraints. So other types of constraints would include Brownian excursions. So Brownian excursion is like a Brownian bridge with the additional constraint that it must remain positive during the remaining time. If I draw a typical trajectory of Brownian excursion, it looks like this. So you have the time horizon Tf, this time is its position, trajectory that is strictly that is positive and must come back to the origin after a fixed time. And so you get this sort of effective potential, which encodes this constraint. And then you have Brownian meanders, which is the same as Brownian excursion, except that you do not have anymore the pinning condition at the end, so you must remain positive up to some final time, which looks like this. Okay.
In what sense are these processes the same as the process of Brownian motion conditioned on returning?
So these are the same in the sense that if you generate those, it's equivalent to generating free Brownian motion and discarding all the trajectories that do not satisfy.
Also, you mean equivalent also in all the fluctuations?
Yes. Yes. For the Brownian bridge, you can check that the PDF at a given time corresponds to the same, but you can also compute two-point correlation function and check that they give the same result. Okay, so this was for the introduction, and now let me give you the outline of this talk. And the idea is how do we extend this idea to other sorts of stochastic processes? So I will first talk about discrete-time random walks, which is the discrete-time version, and it's quite interesting because we take a general jump distribution which includes, for instance, Lévy flights, and then we'll move on. So we'll go by a higher order of difficulty. We go to the run-and-tumble particle, which is non-Markovian, and we will see how to extend this sort of effective Langevin equation picture to a non-Markovian process. And then finally, we will move to resetting Brownian motion, which contains two sources of noise, one induced by Brownian motion, the other one by the resetting process. And we'll see how we can write such constraint effective equations, and this process is out of equilibrium. We will highlight a nice mechanism that we found by surprise in these sorts of process induced by the bridge constraint and the resetting process.
Excuse me?
Yeah.
Before going further, can you suggest some similar mechanism for the discrete time and discrete space random process?
Yes, we'll be able to discuss this case.
I mean, the previous case, the Brownian or...
Yes, so in this first chapter, discrete time, which will also include discrete space, we will be able to take whatever term distribution, it will include this case, and I actually have an example on this topic. Okay, so a free discrete time random walk, xm of t, it evolves according to this Markov rule. The position at step m+1 equal previous position plus some jump, and these jumps are IID random variables drawn from a distribution f of theta. So we'll take an arbitrary jump distribution, f of theta, which also includes, as I said, Lévy flights when it has overload tail mu, where mu is the Lévy index between 0 and 2. It can also be a discrete one to include discrete space processes. Okay. So what we want to do is to generate only bridge trajectories. So we fix some discrete time horizon little l, and we want the process to return to the origin by this time. So typical bridge trajectory looks like this. It returns after little n step to the origin. So the motivations are in behavioral ecology. For instance, when you will look at experimental data of animals moving, you only have discrete times. It also has application in mathematical finance, and in general, these trajectories, they are rare. For the case of Brownian motion, they would come with probability that decays like 1 over square root of n for large n, and so this fits into the case of how to generate rare trajectories. Okay, so let me first give you some possible ways, just out of the hat, to do this. We could draw free trajectories and discard non-bridge ones. This is not efficient. For the Gaussian, specifically for the Gaussian jump distribution, we can use the same mapping as for Brownian motion, and this is shown to be correct statistically, but this only works for Gaussian jump distributions. And finally, which has already been done in some previous papers where they had to do such constraint simulation, they do some Markov chain Monte Carlo simulation of the full joint jump distributions, eta 0 to eta n-1, with this sum equal to 0 constraint, which is the bridge constraint. However, this can also be computationally expensive, and one has to check convergence of such methods. So the question is there a generic efficient method to generate bridge discrete time random walks? And so let me give you our results. The result is yes. And what you need to do is replace the jumps distribution by an effective jump distribution, which will encode the bridge constraint. So this effective process here, this jump distribution satisfies this jump distribution, which depends on the previous position, xm minus 1, the current time, and the full time horizon of the bridge process. So this effective process is no more Markovian, and its jump distribution is given by the free jump distribution times here a correction, which is the ratio of this backward propagator, which I will explain just later on. So this is the main result for discrete time random walks. And let me give you how we obtain it. So essentially what we do is that we look at the bridge propagator. So where we ask what is the probability that the bridge process here at time little m is located at xm. And so due to this Markov nature of this process, we can decompose it into two parts. The first part, for the particle to be there, it must first have propagated from 0 to xm with m steps, and then it must have propagated from xm to 0 during n minus m steps. And these trajectories are independent due to the Markov nature of this discrete time random walk. And so we can say that this probability is the product of the first probability of the first trajectory times the probability of the second trajectory. And the ratio here is normalization, which includes all the trajectories that go from 0 to 0 at step n. So the first part is called the forward propagator because the dependence in x is the final position of this branch. And the second part is called the backward propagator because dependence of x here is the initial position of this branch. Okay. And so those forward propagator and backward propagator, they are the propagator of the free process. And so they satisfy rather simple integral equations here, which says that the probability for the free process to be at x at step m, it must first have been at y at step m minus 1 and then jump from x to y. Then we integrate over all y. And the backward propagator, if it started at x at step m to go to the origin, then at the next step it will be at y and it must go to the origin doing m minus 1 step and then jump from x to y. Okay. So we have simple integral equations for the free forward and backward propagator, and what we want to find is some integral equation for the constraint propagator being bridged. So what we do...
Sorry, I have a really quick question. So
Yes.
in the optimal control business, people do this stuff called things like dynamic programming and backwards induction and things, and it looks a lot like this.
It shares some similar method, yes.
I see. But this is novel in the sense that they don't do this problem.
This is specific to discrete time random walks. Usually in these sort of problems, they have some objective function which they want to maximize, a reward function, and then they write backwards equation for this.
Your objective function is I want to end at the origin at step n.
You could, but for instance, so this is very specific type of, in this general idea where you put a delta reward function, you would only give a reward if you go back here. But what they do in general is that they put some potential here at the end. You say if you go close to it, then you also get a reward. But here this is just specific to generating bridge discrete time processes.
Did Schrödinger not do these kind of things also? Schrödinger bridges, there's something like that, no?
I'm not aware of Schrödinger bridges, but yeah.
We are in the Schrödinger Institute.
Not just cats.
So what we do is that we start from this equation, we use the integral equation for Q, and then we try to massage it in order to get an integral equation for the constraint propagator, and this you can do by rearranging and identifying. Here you have an integral equation for the constraint propagator with the jump distribution, which is no more the free one, but the constrained one, F tilde, which we discussed previously, and here those Q's are the free backwards propagator. So in a sense, this effective jump distribution, if you want to interpret it, is the free one, and it's modified by saying that, okay, if I'm at y at step m, then I get a weight here, which will be, okay, I still need to go to the origin from y plus eta during n minus m minus 1 steps, divided by the probability that I go to the origin for where I am currently. And this is somehow a general idea between Doob transform. Okay. So here it is applied to discrete time random. So let me give an example now about discrete time. So if we specialize to discrete time, so this is just a lattice walk plus minus 1. Then we write the effective jump distribution. What we recover is still a plus minus 1 discrete time and discrete space random walk, except that the weights here are no more 1/2. 1/2, they are corrected by the position at which you are divided by the remaining time you have to go to the origin. So this is quite a nice result. So it already appeared in the mathematics literature and also here in the paper which talks about reinforcement learning by Gahan. And so you can use this effective jump distribution to generate bridge trajectories numerically. You indeed get a bridge trajectory. You start at the origin, you finish at the origin. And here's a check. You can take some intermediate time and compute numerically the PDF of the position of the particle, compare it to the theoretical one, which you can also compute, and it fits well. Okay, let me just give a second example, which is a bit less trivial. Suppose you want to generate a discrete time Cauchy processes, so your free jump distribution is a Cauchy law. Then you can have the effective jump distribution, which has this form, and use it to generate Cauchy bridges, which look like this. Now comes the question is, you can generate just a Cauchy random variable numerically. There exists some simple method, but how do you generate a jump from this distribution, which looks a bit more complicated? Now there is some simple method to do this, which is called acceptance rejection sampling. You just find a constant such that the free Cauchy distribution is bigger everywhere than this effective one, and then you draw from the Cauchy. You get a point here, and you will accept it with a probability that is the ratio of the blue height over the red height. And this is shown to be exact.
So the effective one is it's still Markov. It's
No, so it is no more. The effective process is no more Markovian. Well, it is Markovian if you extend space and you track at the same time the previous position, the current time, and the future time of the bridge. You need to extend space to make it Markovian. Okay, and then discuss excursions and also meanders, and we can extend the method to those sorts of constraints. More interestingly, we can extend it to a dynamical constraint. So let's say that in addition to position, we also track the area below the process. So we perform the sum of the position of step m, and what we want to do is to generate a bridge trajectory with a fixed area below its curve. Well, this we show that we can also do it, and here we can see bridge Cauchy with 0 area, and you can check here this is a position. This you indeed get a bridge, and here this is the current area, and you also get 0 area constraint at the final time. Okay. So now let's move to the run-and-tumble process, which is non-Markovian process. And here it's quite interesting because the free dynamics look like this. So we are in one dimension, x of t is the position. So the velocity of the particle follows a telegraphic noise. V0 is a constant, is the intrinsic velocity of the particle. And sigma of t is a telegraphic noise. Telegraphic noise simply means that it's either 1 or -1, and then it changes between the two values with a rate gamma. And so if you compute two-point correlation function of this noise, it's no more Dirac. You get here an exponential decay where gamma is the inverse persistence time, and this is what makes it non-Markovian and difficult to study. Okay. And so the main question we had is, can we do can we generate bridge trajectories for run-and-tumble particle, and how will it modify this free dynamics? Okay, so let's specify what we mean by bridge trajectory for such process. Well, here we want to fix initial final position to be at the origin, and on top of it, we want to fix also initial and final velocity, which can be the C plus V0 or minus V0 in both cases. Note that due to the constraint of returning to the origin at the final time Tf and the finite velocity of the process, the particle must always remain in this light cone, which is induced by these two constraints. Okay. And so let me show what we got. We found that we can find an effective process to generate those sorts of trajectories. We still have some telegraphic noise here, except that the rates have now been modified and they are space-time dependent. They depend on position of the particle, its velocity, and time. And so the flipping rate, so if the particle is at velocity plus naught and it wants to go to the other rate, is given by the free tumbling rate times again this ratio of backward propagators, specific to the free dynamics of this RTP, and which we found quite interesting. And so let me just flash how we get these results for this non-Markovian process. So basically it goes along the same line. You try to write how does the constraint propagator look like in terms of the free propagator. So again, you have the process here to a final time Tf, and you ask what is the probability that it's located at x at time t. You decompose it into two branches, one to go from 0 to x at time t, and the other one to go from t to Tf. However, because this is non-Markovian process in the xt space, you need to extend it to the xt sigma space. So you need to account also for the current velocity of the process. So what you ask in addition is that you say it must have some velocity sigma v0 at this position. And then you can write this equation with this first branch and the second branch, take the product, and here is the normalization condition. So, and this forward and backward propagator, in this extended xt sigma space, you can write some Fokker-Planck equation, which are given here. One, both 2 for p and 2 for q, depending on the sign of the velocity, and they are coupled through these tumbling rates. And so, okay. And then you try to write some Fokker-Planck equations for the constraint propagator, and you obtain here some Fokker-Planck equation with effective tumbling rates, which are given by this ratio of this backward propagator. And so if you do this, you can then generate RTP bridges, shown as here. And so here you still have the bridge constraint, and check by taking some time slice that you effectively get the bridge propagator, which you can also compute numerically in this case. Okay. Then we can also show that we get excursion and meanders. Okay. Now let me move to the resetting Brownian motion, which in this case you have two sources of noise. You have so resetting Brownian motion is defined this way. So it follows Brownian motion with some probability 1 minus RDT, and with probability RDT it resets to the origin. So this is resetting Brownian motion, which was introduced by Satya and Martin. And so if I just draw a trajectory of resetting Brownian motion, so it's here. So the particle evolves like Brownian motion, and then you have some Poisson process which puts it back at the origin, and it evolves again. So this is an interesting process because it's out of equilibrium. And we wanted to know if we can write some effective equations to do Brownian, resetting Brownian bridges. So this is not a trivial question because here you have like both randomness in the diffusive part and randomness in the Poisson process, which would stop at the origin. So it's not clear where the constraint will be incorporated in the dynamics. Okay. And so here's what we found. We found that one can generate resetting Brownian bridges by the following equation. So you have Brownian motion here with an additional drift, which is created by the bridge constraint, and also an effective resetting rate, R tilde, which is also generated by the bridge constraint, and which we computed them explicitly, and the formulas are given here. And so here you can see that we can do effectively resetting Brownian bridges. You have diffusive dynamics, resetting, etc., and with an effective drift and effective resetting rate, and you return to the origin at the final time here t equal to 1.
Okay, I haven't understood what the problem is here.
So the question is how to generate resetting Brownian motion with a bridge constraint. So you want it to go back to the origin at time t equal to 1. How you do this? And what we found...
Resetting, I can just reset it.
Yes, so you can reset it right at the end, but if you do this, you will not satisfy the right statistical weight. You know, it will not be the same as if you generate plenty of resetting Brownian motions, and then you only keep the ones that come back to the origin. They will not, your method will not yield the right statistical weight. But it's an interesting point. Okay, and then one famous feature of resetting Brownian motion is that if you think of a target search and you say you have some target here, and you use this process to find it, and then you will see that there is some, you look at the mean first passage time to this target. So first of all, there's probability 1 that you will find it, and the mean first passage time is finite, contrary to free Brownian motion. On top of this, it is minimized for an optimal resetting rate. You will minimize the mean first passage time to find this target. And we're wondering if this mechanism is still present for when you have an additional bridge constraint. And this is totally not clear because if you simply naively look at this picture and you put some target here, well, it seems that resetting will hinder the probability of finding it because it puts back the particle to the origin. On top of this, you have the bridge constraint to go back here at the origin. And what we found is that indeed, the main question was, is resetting still a good search strategy in the presence of the bridge constraint? And what we found is yes, and this was quite surprising to us. And so let me show you how we highlighted this fact. So we computed a few search observables. So the first one, which characterizes the fluctuation of this process, is the mean square fluctuation. So the first moment is 0 by symmetry. And so we computed this quantity explicitly. And here's the scaling function, this function f. So a is rescale time. So the red curve is without resetting, which is totally asymmetric due to the bridge constraint. And then we increased a little bit the resetting rate. So capital R is the resetting rate. And you see that you break, as soon as you turn on resetting, you break the symmetry because you break symmetry when you create resetting. But you see that this mean square fluctuation, they are bigger than the case where you don't have any resetting, which is quite surprising. But then, okay, if you increase further the resetting, well, you localize more and more the process and you stay close to 0. So essentially, there is this maximum here, and if you plot it as a function of the resetting rate, which is done here, you see it as a maximum. So it seems that there is some optimal resetting rate to maximize the mean square fluctuation. And this, we were quite surprised about this. So we said, okay, maybe this is specific to the mean square fluctuation, and so we went on and computed other observables. So let's now look at the hitting probability. So m is the position of the target, and what we ask is what is the probability that during the bridge process we will find it. And in this rescale form, we see again that there is an optimal R star that will maximize the hitting probability, which is given here. So it seems to be quite robust, but just to check, we went for a third observable, which is the expected maximum along the bridge trajectory. And so here it takes the scaly form, and again you get an optimal resetting rate. Now, of course, the rates, they depend on the sort of observable you are looking at, but the interesting thing is that they exist. And so we went in high dimensions, also to check, and here's the fluctuations depending on the dimensions. So d equal to 1, 2, and 3 for various resetting rates. and it is still present. The green curve is above the blue one. And so the mechanism which is related to Martin's question is that turning on resetting enables the particle to return to the origin by a last minute resetting. So essentially the reason why there is this optimal resetting rate is that if you have TF here and you have resetting, well, you allow for the particle to be very far away, close to T equal to TF, and then come back with a resetting. So this is this last minute reset which enables this mechanism, which we found quite interesting. Okay, so let me conclude. So we found here an effective way to generate constrained stochastic processes by generalizing this effective Langevin equation. We found it's quite robust. And there's been extensions of this idea to generate interacting particle systems worked by Satya and Gregory and Kaya. They found an effective Langevin equation to generate non-intersecting Brownian bridges in some particular geometry. And finally, let me mention that there's been future works after our work by Cécile Montus and Alain Mozolo, where they've looked at a plethora of constraint processes. Well, thank you.